Hello everyone, this is part 2 of topic 2.1, rates of reactions. In this video, we are focusing on this final box in science understanding, which is energy profile diagrams can be used to represent the relative enthalpies of reactants and products, the activation energy, and the enthalpy change for a chemical reaction. What you need to be able to do is to draw and interpret energy profile diagrams. Now, before we move on to that, let's look at absorption versus release of energy. Now, energy is a key thing. One of the biggest focus question almost, things that we had to cover in year 10 chemistry was that energy is something that causes rearrangement in the particles within molecules and atoms, so they form new things, products, and that was covered in the chemical reaction chapter. Photosynthesis as an example of a reaction, it requires energy to happen. Sunlight being the energy source, and that causes the reaction between carbon dioxide and water. Both of them have got fairly stable nature, meaning they haven't got much energy compared to the product, which are oxygen, which is something that causes burning, combustion reaction. As well as, say, something that's saved in potato, those carbohydrates, they have got a lot of energy stored chemically, right? So you start from here, and relative to this, you end up here. That's an endothermic reaction example as well. I just mentioned combustion reaction, which releases a lot of energy, and we call that exothermic reaction because you start off with very energy-rich substance like petrol, fuel, gas. Yeah, they have got a lot of energy stored. By burning it, you get products with much lower in energy, but there's a distance there relative to each other. Reactants in combustion reaction have got much higher energy compared to the products. Energy is released, therefore there's a change here. Exothermic reaction. Now, I've been doing this stuff with my hands, but that can be drawn with what's called energy diagram, energy profile diagram. Now, first one, well, let's look at what's the main parts, components of it. Reaction progress is the x-axis. It's kind of like time, but it's not really looking at time. It's just how it progresses. Energy is on the y-axis, so the higher on that y-axis, things have got higher energy. Kilojoules per mole it is. So per mole, how much energy in kilojoule would it contain? Reactants, we are now starting with somewhere much lower here, okay? And products having much higher. So can you see the change and the distance and relative to each other, which one has got much more energy stored? It's chemical energy stored, in this case, product has more. How did that happen? Well, it had to go over the big hump there, the other way, hump there. If you just put the lines next to reactants and products and where it ended up, you can see that energy increased, energy stored increased. So the energy must have been absorbed as well. Now, the energy stored is delta H, it's the enthalpy. In reaction that absorbs energy, if you remember what it's called, endothermic reactions, okay, delta H value is higher than 0 because there was a change in amount of energy stored chemically. There was a positive change in that. So delta H enthalpy is positive. Now, pretty much the opposite of it in this energy profile diagram. First few things are the same. But reactants, it start at much higher place, what's going to happen to it? Once it becomes product, you can see the energy level, energy stored within those chemicals or particles that's involved has got much less. Where did that go? Well, it went through the progress here, and you can see a hump again. So there's a bit of energy required to start the reaction, but after that, a lot of energy was released to the surrounding. So reactants energy level went down to where the products are. That means there was a negative directional change to enthalpy change, delta H that is. Yeah? So in this case, delta H is less than 0. Because it's negative change, energy is released, you call that exothermic reaction. So for exothermic reaction, you would expect delta H to be lower than 0. The top hump part above reactants or product, whenever you're working with, the mountain bit, okay? That is called activation energy, and it's an energy required to activate the reactants to become products. For example, for reactants like fuel and oxygen, for them to start reacting, they have got higher energy. For them to react, you need a bit of spark in the engine, and then as soon as the reaction started, you get a lot of energy out, and then products have got much less energy. If you had catalyst, if you didn't have catalyst, let's go with that, the hump would be much higher, okay? Because it requires a lot more energy to get the reaction going. But if you had, if you found catalyst that is suitable for the reaction, the hump would be much lower. It requires much less activation energy. Therefore, it said that when you have catalyst, it allows the alternate pathway for the reactants to go through to become products. Alternative pathway is a word that keeps coming up. So yeah, make sure you know how to use the word. Just going back to factors that affect the reaction rate again, which was part of the last video. Intensity of light was part of it. And, explanations is again fairly important part. Light increases the energy of particle, and that would allow the change to occur. So starting from the reactant which has much less energy, if you had more light, more particles will be able to go over the hump of activation energy. So more particles will have energy to become the product. Time is also a factor that we haven't been really talking about it. Some reactions just take much longer, but some reactions take much less amount of time to be created. The chemicals are used up and the concentration drops. Therefore, if you left the reaction too long, you might not get as many successful collision to get the product. Well, that's another factor that we haven't really talked about. Okay, there's underlined word there, reaction kinetics. The study of factors that affect rate of reaction is called reaction kinetics. It's just a word that might be coming out or popping out. You see it in the textbook. We also watched a video before. It's a TED Video, how to speed up a chemical reaction and get a date. We'll probably watch that again in class, or you can search up on the YouTube. There's also a flash animation here that shows how orientation is important when it comes to collision theory, and that flash video in that link would allow you to understand a bit better, picture it better. Collision theory of chemical reactions. What is it? It's the effect of these factors which allow you to explain how things change depending on the factors. It's a theory that's based on the premise that the reaction occur, the particles, atoms, ions, and molecules, they are always moving, constant motion, particles must collide to form some sort of product, and colliding particles must have enough energy to start a reaction. Without them, you won't be able to have the particles going over the hump of energy profile diagram. Now, the rate of reaction in collision theory depends on the magnitude of activation energy. If the reaction requires a lot of activation energy, then that rate of reaction will be fairly low. They don't just react normally. The frequency of the collisions, if there were less concentration, not going to be as successful. Energy of the particles, if you didn't have enough energy for the system where those particles are in, they might not be moving fast enough. Orientation of the particles, if say molecules prefer to be face-to-face to form a product. If one was facing the other way, it just bounces off and it doesn't react. How do these affect the collision to be successful or unsuccessful? I believe the page for that is 110 for Essentials Workbook. Well, have a read. Do questions following there. There's another diagram that you might see. This one is a bit different from energy profile diagram. This is more of the present representation of where the population sits. You might see it in the stats classes for math, but this also explains how activation energy and how much energy each particle have affect the rate of reaction. So this diagram shows on this side, so where the big bubble height of that shows the population, number of particles. Okay, the higher the particle is, that shows that how many particles within that range has got a certain amount of energy. If you go to almost zero, that end there, this end, not many particles have got a small amount of energy, and there's a big part there. Big part has got majority of population of the particles having average amount of energy. And if you keep going up on the energy axis, you will see small population that has got enough energy to cause the reaction to occur. Activation energy is drawn as just a line where the green ones are shown. They are the ones can react and make a successful collision to form products. It's a bit like at the party. There might be so many people at the party. Small number of people would have low energy and probably just sitting at the back. Some people are still, or majority, I should say, majority of people were the big companies. Majority of people at the party may be engaged, but not on the dance floor. They're just chatting with each other, still having time. That would a good time. That would be the average people. And then there's much energetic people, and they're not many. They're not many in numbers, but they are so into dancing and all that. They just be on the dance floor and being able to make couples or whatever. Okay. That's the analogy that I always use when I talk about population diagram. Moving on. Activation energy, let's talk about that again. It is the energy required to break the bonds in reacting particles. So atoms and ions can rearrange and form the products. Activation energy is an energy required for the reaction to happen, basically. This energy is supplied by kinetic energy of the colliding particles. So it needs to have certain amount of energy, like what the last few slides were saying. If the particles collide with more energy than the activation energy, the reaction may take place. It's not guaranteed that it will be a successful collision. If it's successful or not is affected by the next one, orientation. The particles must be oriented correctly. orientated correctly. And if the particles are not orientated correctly, reaction will take place even they collide with a, sorry, I did say will take place. No reaction will take place even if they collide with a combined kinetic energy that is greater than activation energy. So orientation is important. In summary, there you go. Only a fraction of the collisions will produce collisions, resulting in product forming. Only some of the collisions will have energy greater than the activation energy and the correct orientation. So those combination, having enough energy to go over the activation energy hump, and also the correct orientation, they are key things for the successful collision to occur. If more collisions occur, there will be a greater number of productive collisions. The rate of reaction will also then increase. Now, have a go at doing question 5 to 8. You might be asking where are the question 1 and 4? Well, should have been done after watching the part 1. But yeah, here it is. That's the end of video. So yeah, if you have any question, ask me in class, and make sure keep writing the question down in your book. All right, see you in 2.2 video.